Hello students, welcome to the course Verilog HDL. So in the previous video, I started off with an example of 4 to 1 multiplexer using data flow operators, right? So today we'll continue the discussion, discussing more problems, examples of the next, okay? So 4 to 1 multiplexer we have discussed in the gate level modeling also. So first what we are considering, so how gate level modeling and data flow modeling difference. Okay, so that we are trying to do with the first three examples. So first one we have seen yesterday. So today we'll do the 4 to 1 multiplexer using conditional operators. Okay, so one of the operators you have learned, ternary operator. Using that also you can model any number of muxes. Okay, so that design and program we will see, and then we'll see the 4-bit full adder. So in that, first one is using data flow operator, a very simple logic equation, arithmetic equation can be implemented as 4-bit full adder. So that part we'll see, and the next full adder second method we'll see in the next video. Okay. So there is a more concise ways to specify the 4 to 1 multiplexers. Okay. So yesterday we have seen one of the concise method, right? Just writing the operators, Boolean expression we have written using operators. Okay. So still we can concise that. Okay. Using the conditional operator. So that part we'll see. So in conditional operator, we described how a conditional statement corresponds to a multiplexer operation. Okay, so when I'm explaining conditional operator, I told that it is analogous to implementation of 2 to 1 mux. Okay, so what we have to do is, now our design is 4 to 1 mux. So one conditional operator means it is a 2:1 mux. So that means you need to build now 4:1 mux using 2 to 1 mux, and that can be written as a conditional operator. Okay, so you'll use this operator to write a 4 to 1 multiplexer. Now convince yourself that this description correctly models a multiplexer. Okay, so just if you look at the statement, you may not understand how it is, so you need to convince yourself. So I will do that part. Okay, so be in tune. Okay, so this first part will not change, IO diagram as well as truth table. Okay, so that's why this is same thing copied. So but when they ask the question, so you could not say it is same as logic, right? In exam everything is new question, so they may not ask data flow also, conditional also. So previously they have asked data flow, means this time they can ask conditional operators. So you could not say as it is, right? So you have to write. That's why I have put over here. So always our design starts with IO diagram. Okay, so you have to write IO diagram. So you can copy down once again 4 to 1 mux. It has 4 inputs, 2 select lines and 1 out. And this is the truth table. So 0 0 0 1 1 0 1 1. Okay, so previously what we have done, so we have written either logic diagram and gate level modeling we have done, or this is Boolean expression we have implemented. So now what I am going to do is, now I am doing a completely new design. That is, I am designing a 4 to 1 mux using 2 to 1 mux. Okay, and just we'll verify this truth table, and that same thing will convert into an conditional operator. Hope it is clear. So now see the next slide, very interesting. Okay, so this is the design. Maybe you have gone through in digital system design, or maybe you are seeing first time. Okay, so such type of designs we will be doing it in frequently in logic design. So that's why, so just try to understand this. Okay, so we are having 3 2:1 mux here to build a 1 4:1 mux. Okay, how the operation here? So just if you see the truth table, so what you have truth table, S1 S0 and the out, right? So just the previous slide only I'm writing here once again to understand this design. Okay, so now first, so here conditional operator, what we will write? First we will write the S1. Okay, so S1 condition will be checked. So what is the S1 condition? So either it will be 0 or 1, only two cases, right? So that's why, so you will have the first case 0 will consider. Okay, so when you consider 0 and 1, so what happens when you consider here 0? So this line will be selected, and when you select 1, the lower line will be selected, right? So accordingly I will write. Fine. So then next case what will happen here? Two select lines, right? So first I have considered 0 now, so it is going upwards. So now here S0 again, it will take two values, 0 or 1. So now first we'll consider the value here again 0, and then next one. So when you consider 0 here, so what will happen when you consider 0 here? The first input will be selected here. So this is the 0th line, right? So that's why output is I naught. Okay, so hope it is understood to you. So now I will keep the S1 0, same thing, so it is in the same upper mux. Now I will take the S1 value, S0 value as 1, so then it will select the second input. So S1 I will keep 0, S0 I will make 1. Okay, so the upper mux I1 will be selected. Okay, so the two combination of the two values of S0 is over 0 1 with respect to upper mux. So now lower mux two zeros we have taken, now we will go for 1. Okay, so now we will consider the one case, so I will put the 1 over here. So when you select 1 here, so this lower mux is selected, right? So this is not selected, so it will come to here. So again here S0 will take two values, 0 or 1. Fine. So if it is taking 0, if it takes 0, so what will happen? So I will select 0 here in the truth table, so it will select the I2 input, right? So this is I2. Okay, so then again S1 I will keep 1 to select the lower mux, 1 is there, and now S0 value I will consider 1. So when I consider 1, I3 will be selected. So see this design of 4:1 mux using 2:1 mux. So now the same, this one modeled as a nested conditional operators. Okay, so hope this design is understood to you. Similar way 16:1 mux can be designed using 4:1 muxes, okay, or 2:1 muxes. Okay, so the basic block in multiplexer is 2:1 mux, remember this. Okay, the very basic block in multiplexer is 2:1. So from that you can build any number of muxes. Okay, so that is the idea. So hope it is understood. So this is the truth table, same as previous one, there is no change. Okay, only the design I have changed it. So now this I am not doing any logic equation or gate level. Okay, so just to show you this design. Okay, so how this works. So this is now modeled. So now previously I have understood 1 2:1 mux means one conditional operator, right? So now such 3 2:1 mux I have, that means I have to use a nested conditional operator. So first condition I need to check S1, so then it should have a nested S0. Again S0 is 0 1, it should be correspondingly true expression false expression, then S1 true expression false expression. Okay, if you remember the conditional operator usage. Okay, so just we'll write the program now. So first part won't change, list of port declarations and all. Okay, so this is the program. So module 4:1 multiplexer using Dataflow and using conditional operator, and you can compare this to gate level, how concise it is. Okay, so previously we have used some name, so now I have changed the name. So now name module name is multiplexer 4:1 underscore character. So this is same, out I0 I1 I2 I3 S1 S0. This is not going to change. Even the port declarations also same, because the IO diagram is not changed, right? So out input I0 I1 I2 I3, input S1 S0. So now just the relationship between input and output, we will use the nested conditional operator. See there. So assign out equal to S1. So compare with that 2:1 mux design whatever I done previously. S1 will be checked. So what is that S1? Just writing S1 means it will take two values, 0 or 1. So 1 means the true expression. So if it comes 1 means this expression will be evaluated. Okay, if it is 0 means false expression will be evaluated. Okay, first I have considered S1 0, then S0 I have taken, right? So 0 I have taken, right? So here now he comes it to 0. So now again S0 is having two values, either 0 and 1. So 0 means false expression, true means 1 means true expression. So what is there in false? I0 first will be selected. So that means 0 0 means I0, 0 1 means I1. So this false expression, right? Next we'll go for 1. So if 1 is there, it will go to this expression. So again here S0 will take two values, 0 and 1. So if it is 0 means false expression, that is I2 will be selected, 1 0. Then 1 S1 is 1 and S0 is 1 means I3 is selected. See here how concise and how beautifully we can write the 4:1 mux using conditional operator. Okay, so don't forget to put the brackets here. So brackets are important. Okay, and colon will be there. So this is the operator, conditional operator, one question mark and one colon, and these are inside, so that's why nested. This is the inside ternary operators, conditional operators. Okay, finally end the module. Okay, so this is the beauty of operators. That's why understanding the knowledge of operators will make your design very concise. Okay, so number of lines of the codes also will reduce. Hope it is understood. Fine. So next part is what? The stimulus module and these things, right? So stimulus module is same as previous. So just you can copy from whatever you have learned in gate level modeling. Okay, the same thing you copy, because in exam you could not say, right? In gate level modeling, same thing you copy, right? So you could not do that in exam. If it comes, you should follow that same hierarchy. Okay, IO diagram, truth table, the design, if you want 2:1 marks, that you can enter. Then this program, then stimulus module you copy, and output also you can take from that. Okay, so hope it is clear. So we'll go to the next one. Before that, we'll summarize this what we have learned in 4:1 multiplexer. In the simulation of the multiplexer, okay, so with respect to both, okay, the data flow equation what we have seen yesterday and today, conditional operator, the gate level module can be substituted with the data flow multiplexer modules described above. Just you can change any of the program, but the stimulus module will not change. Okay, so this is what I told, and the simulation results will be identical. So these two you can copy from there. Okay, by encapsulating functionality inside a module, we can replace the gate level module with a data flow module without affecting the other modules in the simulation. See here, this is the beauty of the Verilog HDL. Okay, so just we have changed the how we describe the things. Remaining IO ports, all these things were changed, right? Just we have changed the name for the sake, or you can keep the same name and you can replace with data flow module without changing the internals, right? So this is a very powerful feature of the Verilog. Even in the advantages of Verilog, we have mentioned that, but that time it was not understood. Now, as with examples we have understood, gate level and data flow we have compared. So now it is understood that it is convinced that, so it is a very powerful feature. Clear? Okay. So now we will go to 4-bit full adder. So this is also same thing we have considered in gate level modeling. So that's why detailed design no need required, right? So there we are doing first time, so I have described in detail. Okay, so in this section we write the data flow description for the 4-bit adder. Okay, compare it with the gate level description that you can do. And in gates we had to first describe a 1-bit full adder, then we built a 4-bit full ripple carry adder. So here such things are not required. So any number of adder you can do it in one single line. Okay, because of the operators. And we again illustrate two methods to describe a 4-bit fill adder by means of data flow statements. Okay, as we have seen in 4:1 mux, data flow equations and operators, conditional operators, as we have done. Same way here, 4-bit full adder also I will show you two methods. First method will be using a simple arithmetic operators, plus minus, okay, and concatenation. And second method is of another type of full adder. So in there we have seen ripple carry full adder. That means output carry out of the previous full adder will be given as carry in of the next full adder, right? That is ripple carry. Okay, but now we will see the carry look ahead adder. Maybe you have heard this term or may not, but anyhow we will be looking at that in the next video in detail. Okay, so that is completely based on Boolean expressions. Boolean expressions is converted into operators. So now this full adder, just we recall. Okay, so what we have learned, so almost we have gone through theory almost 1 week now. So just we better recall the 4-bit full adder. Okay, and just we will show the Verilog HDL description. Again here stimulus module is same as that. Okay, so that also we are not writing here. Clear? Fine. So method 1, using data flow operators. Okay, so what we do is a concise description of the adder is defined with the plus and concatenation operators. It is a arithmetic plus and this is a concatenation operator. So using that we are going to build the 4-bit adder here. Okay, so there are many ways you can do the design. Okay, so in the data flow only we have two methods I am discussing here. Okay, if we substitute the gate level 4-bit full adder with the data flow 4-bit full adder, the rest of the modules will not change, as in discussed in 4:1 marks. So you can, without affecting the IO diagram, port list, nothing. So just you are changing the relationship between. Okay, so the architecture part of the things we are changing. Okay, the simulation results will be identical again. Okay, so stimulus as well as simulation results you can be copy from there. So just we'll see the this one program of 4-bit full adder here. Okay, so first, so the design as it is, it will start. So it starts with the IO diagram, right? So full adder, so this is a 4-bit full adder, just you can make 1 bit. Okay, sorry, we are discussing 4-bit only, so this is the thing. And this is ABC in, okay, and mention like this, it is 4-bit. Okay, so A is of 4-bit, B is of 4-bit, and C in is 1-bit scalar, and sum is 4-bit, and C out is this one. Okay, fine. Then truth table. So full adder truth table, you should be familiar with addition, right? So a full adder means it is an addition. Okay, so same as previously, you can just change the name in small letter ABC in whatever you have in your design. Same thing you copy C underscore in, then sum and C out you have, right? So accordingly you change your names here. Okay, so then you write the 8 combinations because 3 inputs are there. So 2 to the power 3, 8 combinations will come starting from 0 to 7, right? So 0, 1, 2, 3, 4, 5, 6, 7. So 0 means 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Already I have discussed this in gate level modeling, so I will not go in discuss. So here 0, 0, 1, you will have 1, 0, 1, 0, 1, 0, 1, 1. Two ones are there, that's why carry will come here 1, and this is 0. 1, 0, 0, you will have 1, and this 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1. Okay, so just you can note down. Okay, so the IO diagram and truth table. Okay, so now need to write now expression also for this because I'm just using the arithmetic now. Okay, so what is that? Okay, so just will show you with this example. We have done 4-bit addition, right, previously. So I will show you here 1 1 0 0. Okay, 1 0 0 1, something I will take. Okay, so I will do the addition here. 0 plus 1, 0 0 0, 1 0, 1 1 1 0 1. Okay, so you have taken 4-bit, one more bit is coming, this is the carry out. So now to do the addition, I will use the operator plus here. Okay, and to do concatenation here, C out and sum. Okay, so C out is the last bit, right? So C out along with sum only I have to write. So C out comma sum, and if I put the concatenation operator, so sum will be here only. Okay, so together it will be noted down the final result. Okay, so 4-bit sum will be there in this one, and 1-bit C out will be here. So the answer is 10101, like that it will display. So this is equal to the output we can show. Clear? Okay, so that is the idea of this, okay, program. So just you see the program now, hope it will understand to you. So define a 4-bit adder, you are using data flow statements. Okay, so module name the same I have given, full adder 4. Okay, sum C out ABC, this is not going to change, same as that. And even the IO port declaration same. So 4-bit 3 is to 0 vector, output 3 is to 0 sum, output C out, this is a 1-bit, input 3 is to 0 AB, you can give a space here. Okay, so 3 is to 0 A comma B, so space is missed here, so space you give. It is a vector. Okay, both A and B of 4-bit. Okay, and input C, so this is also 1-bit scalar. So now just we have to write. So earlier what circus we have done, we have written the Boolean expression, simplified it, and then gate level diagrams you have written, and then call the gates, right? So we may be used the 2 XOR gates, 2 AND gates, and 1 OR gate, right? And in the exercises also you have seen 1 full adder. Okay, so 1-bit full adder we have seen with basic gates, right? So now nothing is there, so just operators are there in your hand in data flow modeling. So just what I have done, A plus B plus C I have made, and that value is assigned to this here, assign. Okay, so together it will hold the value of the output. Sum will have the 4-bit sum, and C out will have the carry generated from this addition. Simple assign. So this is the concatenation operator. Okay, so it can have any number of operands. So here 2 operands it has, C out and sum, and A plus B plus C in. So this is the arithmetic operator, arithmetic add operator, right? So plus is the symbol, and these are the names ABC. So just we have added it. So you have this statement, you can do it for n number of adders, not only 4-bit. Clear? Fine. So with this we are completing the 4-bit full adder using Dataflow operators. So again, I am suggesting you copy the stimulus module and write it here in the notes when I give the questions, assignment questions. So don't forget to include that. Okay. So stimulus module and simulation output of that. Okay. So these two, so you have to do. Clear? Okay. So in the next video, we'll see the second design of 4-bit full adder only, that is using carry look ahead adder. Okay. So this you may not be gone through as per my idea. That's why first I will take the detailed design. Okay. Design understanding is very important in Verilog. Okay. Writing program is just within a 1 or 2 minutes you will write. Hope. Okay. After writing so many programs, you got some confidence now how to write module name, list of ports. Okay, then port declarations, in between variables are there. Okay, so normal in data flow and behavioral modeling, the in between variable declaration is less because we are not using any gate level diagram, intermediate values to store. No, right, there are no drivers are required. So normally only port declarations and list of ports will be there, and then straight away assign statements will be there, number of assign statements. Okay, so in all the examples now I have used only one assign statement now. Okay, so in the next 4-bit full adder, carry look adder, I will use multiple assign statement. Even multiple assignment statement also I can write it in single line with the comma operators. Okay, so that also I will try to explain in that example. Okay, so in all the previous three, now 4:1 marks and this full adder, both we have used only one assign statement. Okay, so that means it is a concise description of the Verilog HDL. Okay, so hope it is clear. So whatever I discussed, so we'll see the things in the next video. Okay.